welcome you to our ARCS Foundation Honolulu Chapter Pauhana program. ARCS Foundation is a national organization that supports science in America through unrestricted grants to outstanding college students in STEM fields and health sciences and mathematics. Our Honolulu chapter was founded in 1974, and we've provided about $3 million in support for graduate students here at the University of Hawai at Manoa. So along with the work that we do to raise funds to provide these grants, we also like to learn about the sciences. We're a group of women who are interested in, believe in science, but not necessarily a heavy science background ourselves.
So with that, Roy.
Mahalo, Cheryl, and a big mahalo to the ARCS Foundation for their ongoing support of science and especially astronomy here in Hawaii. My name is Roy Gal. I'm a specialist at the Institute for Astronomy, and I handle our public outreach programs, often in collaboration with ARCS. And just a quick information about the IFA. We're the largest purely academic astronomy unit in the country, with about 35 faculty now, about 40 grad students, and a burgeoning undergraduate program, and lots of public events. In fact, if you'd like to come out and join us, if you're local, we'll be at the Geek Meet on September 25th at Magic Island, which is a great family-friendly outdoor event. So I'd like to introduce our speaker today, Heidi Hammel. Heidi has a long-standing connection to the IFA, having gotten her degree with us back in 1988. She got her PhD at the Institute for Astronomy after moving here from the cold winters of Massachusetts. She's done an incredible amount of work in solar system science and has received many awards for her work, including ARCS Awards when she was at IFA, and numerous prizes, including the Urey Prize and the Sagan Medal from the American Astronomical Society. And currently, she is the Vice President for Science at AURA, the Association of Universities for Research in Astronomy, which manages many of the National Science Foundation and NASA's observing places like the Gemini observatories and others. So without further ado, here's Heidi to tell us all about JWST.
Thank you so much, Raj and Cheryl, for the introduction. I'm very happy to be talking with folks there in Honolulu. I'm in Virginia right now, where it is not quite as nice as it is where you are, I guess. But last week I was in Hawaii for some work on Maui and then a visit to Kauai. So it was nice to be back in the islands again. Let me see, I'm going to share my screen, and can I see a thumbs up if it looks okay from people? Great. All right, so today I'd like to share with you some new views of the cosmos with the James Webb Space Telescope. And we'll talk first a little bit about science. I have to give you some science background so that you can appreciate what it is I'm going to say. And then we'll talk about the telescope, and then we'll show the new images. So let's roll with the science. And I'm going to start by figuring out which button to press to make it all work here. How about that one? There we go. Light comes in many colors. Isaac Newton was one of the people who helped establish this for us. In this etching, you can see him holding a prism up to a pinhole in the wall, and the white light from the sun was spread out into the beautiful rainbow of colors that we call visible light. But what's important for us to know for this talk is that the visible portion of the spectrum is just a very small piece of it. That there is light at wavelengths that are redder than red. There is also light at wavelengths that are bluer than blue. And you probably have heard of some of these kinds of light: radio waves, microwaves, visible ultraviolet is why we wear sunscreen when we're in Hawaii. The X-ray, of course, you are familiar with that from visits to a doctor's office, and high energy gamma rays. But the part of the spectrum that's really important for JWST is right there labeled mid-infrared and near-infrared. Those are the wavelengths of light that JWST will be studying. And I'll talk about exactly why we chose those wavelengths in just a few minutes. Hubble, as an example, is a visible wavelength telescope and a little bit of ultraviolet as well. And the universe emits light at all of those wavelengths. It doesn't just emit light at visible wavelengths. And so astronomers want to use all the wavelengths of light to study objects up in the sky, in the universe. And we want telescopes that can sense all of those wavelength ranges, from the radio through the visible all the way out to gamma rays. And so that's important point number one. We want to get all the light at all the wavelengths, and James Webb is going to focus on near infrared. Here's another very important bit of science that I need you to be aware of. When we spread that light out into that rainbow of colors, certain molecules will absorb some of those wavelengths of light, depending on their temperature and their pressure and other characteristics. And so we can, when we see the missing lines, we call them spectral lines. When we see those missing lines, that tells astronomers that there's a molecule there of a certain characteristic, a certain composition. Also, some molecules, depending on whatever their pressure, temperature, or whatever is, light at specific wavelengths, very narrow bands of light. And that's what I represent here as white lines. And it's cumbersome to be showing these rainbows of colors all the time. So what astronomers do is they plot the wavelength on one axis of a graph, and they plot the brightness on the other axis of the graph. So that middle plot that you see there as a rainbow with dark lines and bright lines would look something like this. And this is a spectrum. That's what we call spectrum. And by those specific lines, whether they're bright or dark, and where their locations are as a function of wavelength, that is how we probe what is out there in the universe that we can only see remotely. So if you've ever wondered, why, how do astronomers know that stars are made of hydrogen and helium? This is how we know, because we look at the spectrum of light and we look at these specific lines. So here's an example, just to back up what I'm saying. This is a beautiful image from the Hubble Space Telescope of an exploding star called Eta Carina. And it's a lovely image. Astronomers like images, but astronomers even better like it when you take that light and spread it out into a spectrum, because then we can see that what is causing that light, the materials that are there, are helium, argon, iron, nickel. All of that chemistry is encoded in the spectrum. So a spectrum is science. And I'm harping on this because you're going to see a lot of spectra coming from JWST, because it is like the bread and butter scientific stuff. There's great images, but spectra are so important. That tells us the composition, temperature, pressure, even the dynamics of things happening in the universe. All of that comes from spectra. And so that's why we talk about spectra. Let me have one more foray into science before I get into the telescope. And that is spectra have told us about a phenomenon called cosmological redshift. And this is crucially important for why we built JWST. That's why I want to share it with you. For a nearby star, it may have a pattern of hydrogen lines that looks like this, and we label them with Greek letters, alpha, beta, gamma, delta, epsilon, et cetera, et cetera. But we've discovered over the decades, or centuries actually, that if you look at a nearby galaxy, those spectral lines are shifted just a teeny bit. And it may be a little hard for you to see here because they're almost lined up. But if we go to an even further galaxy, then you can clearly see how all of those lines are shifted out into the red. And a super, very far away galaxy, like at the edge of the known universe, is shifted way into the red. This is because our universe is expanding. This is something that Edwin Hubble discovered, promoted, and that's why Hubble Space Telescope is named after him, because of this discovery. He discovered that the universe is expanding, and as it expands, the wavelengths of light are expanding as well. And so longer wavelengths of light are redder. And so the further you go into the distant universe, the more shifting you have into the red. And so what that means is that to be able to see the very first galaxies that ever formed in our universe, we can't look at visible wavelengths. We have to look in the mid-infrared. And that is why JWST is a mid-infrared telescope. It's to find those first galaxies, the first light that formed out of the primordial soup that was the early universe. There's one other important bit of information about infrared wavelengths, and that is that you can see different things when you look in the infrared. Same object, different wavelengths. Here's a fellow holding up his arm, and he's got a black garbage bag over his hand, and you see the black garbage bag. But if you looked with an infrared camera, this is what you would see. The infrared camera probes right through that garbage bag and allows you to see his hand inside the garbage bag. And we use this phenomenon in exactly the same way in astronomy. And for those of you who are amateur astronomers, you might recognize this constellation. This is the constellation Orion. And Orion is known because is a very popular target for astronomers, primarily because of the little thing, the 3 stars of his belt hanging off of his belt is what we call a sword. And there's a bright patch in the sword that's called the Orion Nebula. When I was a grad student at the IFA, we had brand new telescopes, brand new cameras, and we had an acronym called YAMU, yet another map of Orion. Every new instrument, every new telescope, one of the first things it does is takes a picture of Orion, just to show the advancements of this telescope. When you look at this same constellation in infrared light, this is what you see. You see a vast cloud of dust that is emitting warmth from the heat of newborn stars that are being born inside that nebula. And the Orion Nebula in the visible wavelengths is actually a little tiny hole in the dust that lets the bright light of the stars out. But in the infrared, you can see that there's star formation going on for a huge swath of the sky. And so this is another powerful aspect of JWST. It will allow us to look inside dusty clouds, and you'll see some of that in just a minute. Just a few more things about why we put telescopes in space. There's sort of 3 reasons. So we do have telescopes on the ground at optical wavelengths, like on Mauna Kea, for example, because visible wavelengths make it all the way to the ground. And in the radio, there's a radio window where all the radio wavelengths make it to the ground. But you see that there's other regions, particularly at the bluer wavelengths and in this infrared area here. You can't see my fingers pointing at the screen. I'll try to be verbal. There are wavelengths that never make it to the Earth's surface at all. They're just absorbed by the Earth's atmosphere. And so if you want to do science at those wavelengths of light, you must go to space. That's the only way to sense the photons. And although a little bit of infrared light gets to the ground, it's really swamped out by the Earth itself, which is warm, and our telescopes, which are warm compared to space, the atmosphere, which is warm. So to really do high sensitivity infrared work, we must go to space. So it's in part the atmospheric absorption, as I said, it just absorbs light. You must go to space. And this distortion from our atmosphere as well. Time for another talk, probably. But even in our best sites, like Mauna Kea, the distortion of the Earth's atmosphere messes up our images somewhat, although we are able to compensate for that with using special tricks. And then the sensitivity that I talked about. So let me now turn to the telescope. Here is a little cartoon showing you the 2 powerhouse space telescopes, James Webb Space Telescope on the left and Hubble on the right. So a couple of differences you'll notice. the mirror, which is shiny silver in Hubble and gold in JWST, it's a lot bigger for JWST. It's a 6.5 meter mirror as opposed to the 2.4 meter mirror of Hubble. So right there, you get a huge gain in sensitivity. Those colors, silver and gold, are not randomly chosen. In fact, the Hubble mirror is coated with silver and some other compounds mixed in to enhance reflectivity at ultraviolet wavelengths. Gold is used for JWST because gold is a fantastic reflector of thermal infrared light. That is why we chose to coat the mirrors in gold. It's an extraordinarily thin coating, spread out across the 6.5 meters diameter, that large thing. You can see the person to scale. It's roughly the size of maybe a small golf ball that's spread out in a very extremely thin layer over all of those mirrors, but that's all you need to be a good reflector. Another thing you notice that's different about Webb and Hubble is that Hubble, its whole structure is encased in a big tube, right? Whereas Webb is just out in the open. The mirrors themselves are just like sitting out there in the open. And we do that because that tube actually would absorb sunlight and radiates warmth, which swamps our faint infrared signal from distant galaxies and things. And so we did away with it. All we have is a very thin support structures holding our primary mirror, our secondary mirror, to reflect light back to the instruments in the telescope. And finally, the other difference is this huge structure you see underneath the telescope, the sun shield. That is designed to keep the telescope extremely cold. It is always going to be positioned between the telescope and the Earth and the sun and the moon. And that way we don't have any Earth light, sunlight, or moonlight shining on the telescope. So all of those structural differences are because this is an infrared telescope. Everything was every design decision for creating this James Webb Space Telescope was because of the infrared wavelengths. Okay, so let's move on. And this is mostly for any astronomers like Roy. We are going to be doing both imaging, that's the top. This is a list of our instruments, and also spectroscopy. I mean, remember I showed you what spectroscopy was because it's extraordinarily important. And so these different instruments, NIRCam, MIRI, NIRIS, and NIRSpec, are the 4 main science instruments on JWST that are going to be producing all the images and spectroscopy that I'm going to show to you today. And I started working with this program more than 20 years ago. 2002 was when I wrote a proposal to NASA to be a part of the team to help design the science aspects of this telescope and to advise NASA and the engineering staff on any science-related decisions that had to be made. And that proposal was accepted, and I became one of only 6 interdisciplinary scientists in the world to participate on the science working group for JWST. We have 4 main science themes that you'll be hearing about today. One is, as I said earlier, we want to see the first light from the first galaxies. That was the overwhelming science driver for this telescope. But if you build a telescope that can do that, you can do other science as well. You can actually see the assembly of galaxies over time because you can see galaxies close by, galaxies at medium distances, and galaxies all the way at the edge of the universe. And you can see how they change with time. So evolution of galaxies over time is a second key science theme. A third science theme is within our galaxy and within the closest neighboring galaxies, we want to look at how stars are born and how planetary systems form out of the dust of the stars. And finally, the last science theme is the one that I am most closely associated with. That is studying planetary systems and the origin of life. And this is planetary systems not only around other stars, of which there are now thousands known, but even our own planetary system. In the introduction, it was mentioned that I'm a planetary scientist and a planetary astronomer. So I will be using JWST to look at objects in our own solar system, and I'll share some of that with you. And so Christmas Day was the day that we had been waiting for decades. That was the day that we successfully launched James Webb Space Telescope on an Ariane 5 rocket out of the spaceport of French Guiana. The Ariane 5 rocket was contributed to us by the European Space Agency. This mission is a joint European Space Agency, NASA, Canadian Space Agency mission. All three of those groups have contributed significantly. So I'm now going to show you a video from down at the spaceport at the time of launch, and it'll be loud, and I might make some comments, so hopefully you can hear them over that. This is in French because it's a French spaceport. It only launched once, and there's some different views of it.
Décollage liftoff from a tropical rainforest to the edge of time itself when James Webb begins a voyage back to the birth of the universe.
This lady shows what I was doing, hyperventilating.
Punching a hole through the clouds. 20 seconds into the flight, good pitch program recorded. Orion 5 rocket continues to fly uphill in nominal fashion.
We were all shedding tears at this moment, you know, tears of joy, tears of nervousness. It's a big, big rocket that our precious telescope was launched on. The Ariane company actually put a small camera inside their rocket fairing so that we could actually see the separation of the telescope away from the rocket. And so that's the next video that I'm going to show you. It's our last full view of the telescope by humans. And kind of another one of those sort of tearful moments for many of us. Hit start. There we go. So there the telescope goes. It's all folded up in a package to fit inside the rocket. And you can see the little rocket engines firing on the back of it. There's the Earth in the upper part. That is a solar panel deploying so that we have power for this spacecraft. And this is the last time that we've had a close-up view. It then started on a long journey. It was journeying from the launch site in French Kourou to a point that we call L2, a Lagrange 2 point. And during that month-long journey, that package that you saw all shiny had to unfold and open and deploy in about 500 different ways. And 500 is not an exaggeration. It is about 500 different ways. And so very complicated process to get us to our fully deployed telescope like you see at the bottom. And why are we sending it so far away to that L2 point? L2 is located if you drew a line from the sun to the Earth and then keep going for 1.5 million kilometers, about 1 million miles. That is the L2 point. It's a gravitationally stable point. When you put a spacecraft in a little orbit around there, you need very little fuel to keep it in that position because of the way the Earth and the sun are lined up in terms of their gravitational pull. And so we put it there, first of all, because it's a gravitationally stable point. We don't need as much fuel. But more importantly, we put it there because that makes it far away from the sun, the Earth, and the moon. And here's a picture of JWST that sometimes you see pictures that look like this, but that's actually not the right orientation. This is the orientation with the sun shield always blocking out the sun, the earth, and the moon. It was designed to be large enough to be able to block out those three celestial bodies. And we always travel with it in that orientation around the sun, always. So we can map out the sky in sort of a donut shape. If you can imagine the telescope turning on its axis, you never move the sun shield out of that position, but the telescope can rotate. And then over time, we just move around the sun, always keeping the sun shield in line with the earth and the sun. So over the 1 year, we can map the whole sky, right? But we can never look backwards, all right? Because we can't, it's too warm and too bright. It would just destroy our sensors. And because we can never look backwards, we will never have JWST images of the moon. We will never look at Mercury. We will never look at the earth, and we will never look at Venus. They're all too close to the sun. Anything else in the solar system and beyond to the edge of the universe is fair game to JWST. So after a month, we got to L2, we're deployed, we're going in our little orbit, and then we spent 6 months calibrating all the instruments. And this is a chart from a blog I wrote about it. And if you're interested in how we calibrate and why we calibrate, I can share the blog information for you. I'm not going to go through it today, but suffice it to say, it's a complex telescope, and we had to focus the mirrors, we had to focus the instruments, we had to check out all of the modes to make sure it was all working. And in fact, it was. It all went so well that every week we were like, I can't believe it's going this well. We're still on schedule. Everything is going perfectly. And so here are some images from some of the instruments showing you how the telescope looks. And I wanted to pick out the one in the upper right from the MIRI instrument, the mid-infrared image, and show you why we're so excited about this telescope by comparing it to 2 other infrared space telescopes that have been launched before, and give you a sense of why this telescope is so amazing. On the left is the WISE telescope. It's an infrared telescope that was launched a while ago. Subsequently, we launched the Spitzer Space Telescope, which you can see is better than WISE. But on the far right, you see James Webb Space Telescope. And I hope you can appreciate the quality difference from the left to the right. It gives you a sense of just how much more we can see with James Webb that we just simply couldn't see before. We could see there were stars there, but we couldn't see the background stars, and we couldn't pick out all the dust environment. This is all due to the large aperture, the large mirror size of JWST compared to these earlier telescopes. So it's a huge improvement. So let's talk now about those first images, which is really what you wanted to see. You didn't want all the science, but you had to have all the science to appreciate it. So the first James Webb Space Telescope Deep Field. So here's the picture. And what you're looking at here is a 12.5-hour exposure looking at a cluster of galaxies. And there's a few stars in there. Anything that has those really bright, spiky things sticking out of it, we call those diffraction spikes. Diffraction spikes are typically found on point sources like stars, but extended objects, fuzzy things, those are galaxies. And the white stuff that you see in the middle there is the galaxy. I'm going to zoom in, and you can see how many white blobs there are. Each one of those white blobs is a galaxy made of millions of stars. But if we slew off to the side there, every one of those things that you see that doesn't have those sharp diffraction spikes is a galaxy made of billions of stars. It's astonishing. And this was only 12.5 hours. The Hubble Deep Field was 10 days. So that gives you a sense of the sensitivity of difference between JWST and Hubble. And some of these objects, particularly the littlest and the reddest ones, those are some of the most distant galaxies that we have yet ever seen with and Webb is shattering records as we move forward here. Let me see. This is a Hubble image of the same field. And you'll notice how many of the galaxies are still there, but many of them have disappeared. And so I'm going to go back to Webb now to give you a sense of how much richer the Webb field is compared to Hubble. A lot more to see. So here is an example where we pull out several different galaxies and we show their spectrum. You remember the cartoon that I showed you, which showed you how the spectral lines marched off to the right? You are actually seeing this, but with real data here from the James Webb Space Telescope, where a galaxy that is only 13.3 billion years old, at the top, you can see that cluster of different hydrogen and oxygen lines over near 2 microns. But as you step through time, you see that cluster moves off to the red. This is exactly what we had expected, and we can pull it out here. And just the one thing I want you to take away from this is that, like that bottom galaxy, which is just a little red dot there, 13.1 billion years old. And yet with this telescope, I can tell you that there are hydrogen atoms in this galaxy and oxygen atoms in this galaxy that is at the edge of the universe. That's the power of James Webb. That's what we built it to do. People have been having a field day with this. Lots of papers have started to come out where people are claiming hugely distant galaxies. Some of them are not confirmed, but some of them are confirmed. One of these galaxies, a little red dot like this, called Glass Z13, that may have formed only 300 million years after the Big Bang. This is a baby picture of the universe. Hubble gave us high school yearbook pictures of the universe. Webb is giving us the baby pictures of the universe. And it's by putting them all together that we actually try to understand how our universe formed and evolved to where we are today. Here's another spectrum, just to give you a sense of the richness. This is another 13.1 billion year old galaxy. And in its spectrum, you can see not only hydrogen and oxygen, but you see neon. Even neon had formed at this time, at this age of the universe. And so this is the kind of rich science that our various teams are going to be working on for years to come. So that's just our first deep field. That's just one set of data. And this is not even the actual deep field. This is a preliminary deep field pointed at that galaxy cluster. We do have planned very deep fields to complement the ones of Hubble and other telescopes. So it's just a very exciting time to be an astronomer. Let's talk now about the birth of stars. This is a really beautiful image called Cosmic Cliffs. That's its artistic name. In fact, it's a piece of the Carina Nebula, and it's taken at 4 different wavelengths that have all been composited together to give you this beautiful color image. And what you're seeing here is you're seeing the edge of a very large cloud of dust. And up above this image, out of the field of view, you can see some diffraction spikes from a very bright star. The bright stars that have been forming in this cluster have been just blowing out against the dust and pushing it away. But sometimes when it pushes away, it encounters dense areas like the clump that you see sticking up there. What that is a high density clump, and inside that clump and some of the other clumps that you might see as we scan along, there are stars being born out of the dust. And it's higher density there because these stars are collapsing and forming into very rich star formation regions. So that's what gives this sculpted shape, is variations in the density of the dust that is being pushed away by the super bright stars up above. Now, this is some near infrared wavelengths where we are seeing some of the scattered light off of the dust. But if we go to our JWST's longer infrared wavelengths, remember the garbage bag? Remember how you could see through the garbage bag to the arm in between? Well, what you're going to see now is transitioning to a longer infrared image where you can see through the dust. So watch as that happens here. Did you suddenly notice that a lot of stars, yellow stars, appeared in the middle of that image that you couldn't see before? That's what was happening. The infrared wavelengths are penetrating deeper. And so let's zoom in a little bit on this. And you can see a lot more stars. You can effectively, you're seeing through the dust. You see how you see way more stars down below compared to the other image, which all you saw was wall of dust. And so that allows us to probe deep into some of these star formation regions and truly get a handle on the processes that are taking place there. And here's a new image that just came out about 4 or 5 days ago. It's another beautiful star forming region. This one is in a place called the Tarantula Nebula because it kind of looks like a spider to some people. And in here is a really bright burst of brand new stars. The blue ones are brand new stars. That yellow star with the bright diffraction spikes is a foreground star who's not related to the cluster at all. It's just photobombing this image. So again, there will be many, many more beautiful images of planetary, of stars and as they are forming. The folks who are working on the birth of stars, they're very happy with these data. Okay, let me talk then about the end stage of a star's life. This is a beautiful circular nebula. And when these were first discovered, because they were circular, the early astronomers who found them thought they might be related to planets. So they called them planetary nebulae, but they're not related to planets. What these are actually the death throes of a star that's collapsing and throwing off huge shells of dust. And that circle that you see is a shell of dust being blown out by a central star. This is a Hubble image of the Southern Ring Nebula. Let me show you now our new JWST image of the Southern Ring Nebula. And you could see a lot more detail, a lot more structure in terms of the morphology. There's multiple shells now visible, and that by studying these multiple shells and the order in which they've been released and the structure, we will get more information about the final life cycle of the particular star that emitted them. And there's a special surprise revealed by JWST when it was looking at this image, because if you look at this image, you see there's a star right in the middle, and you would say, aha, well, that must be the star that is doing this exploding and shedding of shells. But in fact, the mid-infrared images of this nebula with Webb showed something surprising. And that is, if you zoom in and then switch to the mid-infrared, look what happens. A second star pops out. That yellowy looking star, that is actually the star that is emitting all these shells. The other star just happens to be nearby, probably in the foreground, just a chance superposition to put it near the center. But it's actually the other star that is creating this fabulous nebulae. That was a kind of fun result from JWST. So let's talk about planets around other stars. We now know that there are over 5,000 planets around other stars with a variety of ways of finding them. But one of the key ways is looking at what's called a transit. And that's when the planet crosses in front of its host star and has the starlight blocked out. And that tells you there's a planet there by the little chunk of light being removed as a function of time. And you can see in the middle image, the starlight is shining through the atmosphere of the planet. And by looking at the spectrum of the star and the spectrum of the star and planet, and subtracting the two, you are left with the planet's spectrum. So this is a technique that allows us to probe the spectral characteristics, the composition, pressure, temperature of planets around other stars. Transit spectroscopy, it's called. And this is one of the first planet transits that was released, showing you those bumps being indicative of water vapor in the planetary atmosphere that was being sensed. This is a planet called WASP 96b.
It's unbelievable, the size.
Yeah, and so that you can see that water there. Another new result that came out, this one's a little complicated, but I wanted to show it to you because it's really very cool. Here you can see on the table, a whole, on the left, a whole pile of those transits. Each one is at a different wavelength. And so by comparing the depth of the transit as a function of wavelength, you again can pull out the spectroscopy. And the quality of this was just exquisite. On Twitter, I found someone who simulated a different visualization of this. So it isn't just a plot, it's sort of a 3D visualization where you've got wavelength on one axis and you've got the color on another, and then you've got the depth on the third. So I just wanted to run that, and because I thought it was a really interesting way to visualize this. You start off and you can see wavelength on one axis, time on the other. So you can see all of them piled up next to one another, and you can see how the transit depth varies. And that variation of the transit depth is what gives us the spectrum of the planet. All right, so that's how we pull the chemistry out of these transits. And here's the spectrum, an absolutely super clean detection of carbon dioxide in this planet atmosphere. So we're going to be using this technique not only for water and carbon dioxide, but all other manner of chemicals in the atmospheres of these exoplanets. So it's an amazing tool. Let me talk about exploration of galaxies. Here's a beautiful galaxy image that was released by Webb. It's called Stephan's Quintet. There are 5 galaxies in the picture, 4 of them on the right-hand side, and then a 5th one on the left. And if you look closely, you will see that the galaxy on the left is a little different than the others. It's not as smooth and milky. You can actually see the individual stars. This is a foreground galaxy. It is not part of the other galaxies. These other galaxies are more distant, and they are physically interacting with one another. You can see in between them how in those there's these ranges of red, which is star formation. And off to the side, what you see is lots of other galaxies. Every JWST image is like a Hubble deep field. So there's going to be so much galaxy science going on. So this is a visible wavelength image, but let me show you the mid-infrared image. That shows you where the star formation is happening. This is the hot parts of the galaxy here. This is what's hot. And so you can see when things are interacting, and in the cores are where these galaxies are hot. And we can also do spectroscopy of these cores and pull out not only things you've heard me say already, like hydrogen, but also silicates. You know, these are like rocky things. And iron. You see the spectrum of iron in the cores of these galaxies. So a lot of interesting work will be done studying these galaxies. And I wanted to show one more galaxy picture you may not have seen. It's a comparison of Hubble image in the blue with the JWST of the same image in the red. So in the Hubble image, the dark lanes of dust, they light up like fireworks in the red. And so that tells us that star formation is taking place in the vicinity of those dark dust lanes in the Hubble images. So I want to finish my little tour of JWST images by talking about some of the work that I and my team have been involved in, and that's our local neighborhood in the solar system. One of the first images we ever got of a solar system object with Webb is of the planet Jupiter. And you might ask, and it would be a fair question, Why should we look at Jupiter with this special astrophysics telescope since we send missions there and orbiters? We have an orbiter there right now. What can JWST do that you can't do with an orbiter? Well, a couple of things. First of all, with our infrared cameras, we can sense auroral activity in the northern poles of this planet. And we had seen aurorae before with Hubble at ultraviolet, but we're seeing a different phenomenon here, that red stuff that extends above the disk of the planet, extends above the cloud tops. That's an extended auroral emission that we had never seen before we had JWST. So that's a new discovery. And you can see a similar kind of phenomenon down in the southern pole, where you can see that extended auroral emission. So this complements what we had learned from our Voyager missions, from the Galileo mission, from the Hubble observations. It complements it and extends it. Another very, very surprising discovery was on the limb of the planet. Do you see what looks like a separate line, like a double edge there? When we first saw this image, everyone's like, oh, must be out of focus. It's not out of focus. So what is it? Well, we don't know. We've never seen that before, not even with spacecraft. And so we've got two competing theories right now. One is that it is high altitude auroral glow at some high altitude. Another idea is that it is a haze layer that is detached from the deeper clouds. And it's going to take more observations to really sort out which those two it is. But it was a surprise. And it just goes to show, even if you've sent multiple spacecraft to a planet, you can still be surprised when you have a fantastic telescope like Webb. And of course, the great red spot. This is just a beauty shot of it. Why is it not red? Well, because this is not visible wavelengths, right? This is infrared wavelengths. And so it's not red because we're not looking at the visible wavelength spectrum. Why is it bright? It's bright because it has high altitude clouds over it. And at these wavelengths, most of the planet has absorption from methane in the atmosphere, which makes it dark. So the only way you get bright areas is if you have high altitude clouds. And so the great red spot and the equatorial band and lots of sparklings of high altitude cumulus clouds appear bright in this near infrared image. So there's tons of science that we're going to be doing with this and many other kinds of observations as well. And I wanted to show one last Jupiter image. Not only did we take this close-up view, we did a wide field view at a slightly different set of wavelengths, so the color's a little different. But I wanted you to see that, because what is immediately apparent in here is you can see the ring system of Jupiter off there to the left. You see a tiny moon, Adrastea, at the tip of the rings, but you can see the curve of the ring reaching right up to the edge of the planet. And what's astonishing about this is that those rings are 1,000,000 times fainter than the planet itself. That is how amazing the dynamic range is of the telescopes, of this telescope, James Webb, that we can see things next to one another that have, 1,000,000 times difference in brightness. And we see other things, other moons, we see diffraction spikes. There's a whole program devoted to Jupiter science. And if you have questions about that, I'm happy to answer them, talking about some of the other moons that we will be observing, my team and another team studying Jupiter. So that's just one sampling. Stay tuned over the next 2.5 weeks. There should be more interesting solar system science coming out, which may include some of the following: asteroid spectra, comet spectra, Mars images and soon spectra, Neptune images, Kuiper Belt object spectra, and so much more. We have only started. It's like I'm on the edge of a fire hose right now, and every day it's like new data. So it's really amazing, and we're just getting started. I mean, we are only a few months into operations, and we're going to go for. We originally were scheduled for 5 years. with hopefully an extension to 10. But because our orbital insertion from that Ariane rocket was so perfect, we now have fuel for at least 20 years of observations. Now, our telescope may not last 20 years because it's out there exposed to outer space and it's a rough environment out there. And if you have questions about that, I can talk about it. But, you know, we have at least 5 years, probably 10 years. And I'm just showing you the stuff that's happened in like the first 3 weeks. So it's going to be incredible. So this is the science that we plan to do. I showed it to you before. I will share with you that with Hubble, when we now look back with a 30-year perspective and ask what has been the most important science in the 30 years of Hubble operations, only half of it was science that we'd planned to do, like I'm showing you here for Webb. And so the other half is science that we, the scientists who help advise and build the telescope, we didn't even think of. And the same will be true for Webb. I don't even know what the most amazing science is going to be. I know what I want to do, but there's going to be more that young whippersnappers coming out of the IFA are going to have ideas, and they're going to just, you're going to blow us out of the water. It's just going to be great. It's going to be great. So I just wanted to end again with this slide. I wanted to zoom in on one piece of it. These arcs that you see, because you guys are arcs, these things that we call these arcs as well in astronomy, these are refocused images of distant galaxies. And even in the refocused images, we can pull out clumps that may be stars or clusters of stars. And so the arcs here are going to help us understand the very distant universe, just like the ARCS Scholars program helped me as a young scientist to develop my craft so I could share this with you today. So I just wanted to sort of tie the circle there on the ARCS of you and the ARCS here. So I just want to conclude with this. We're in a new era of astronomy. It's starting now. This is it. And I don't know where it's going to lead, but it's quite an amazing ride. And I am so thrilled to be a part of it. And thank you to ARCS Honolulu for helping me when I was a young student there in Honolulu. Thank you.
Thank you, Heidi, for that fascinating tour. And for the plug, we appreciate that. I forgot to mention in the beginning that you were an ARCS Scholar with 2 awards during your years at the Institute for Astronomy. So we did want to acknowledge that. And I also wanted to welcome, I forgot to welcome some of our members of sister chapters who are with us. We usually call these programs Pauhana because we do them into the day, and it's Pauhana for Heidi because it is the end of her day, but that's why we're at noon Hawaii time today. So thank you for joining us. I did have a question. You mentioned the vulnerability of the telescope and not being in the tube like Hubble. Does that put it at great risk for things that might bump into it?
So it does put it at risk. I don't think I would use the adjective great. We understand moderately well, fairly well, the environment out at L2 because we have put other spacecraft there. So part of the planning for this was the knowledge that there would be micrometeorite impacts on the telescope, on the mirrors, and onto the sun shield. So that was all part of the planning and part of the lifetime assessment. So since we have reached L2, there have been at least 5 micrometeorite impacts already that we've been able to detect. The first 4 were all totally within the realm of expected, very small, can barely detect them. The 5th one was a little bit bigger than we expected and actually deformed one of the mirrors a little bit. But the good news is that all of those mirrors on JWST, behind them have little motors that you can move and adjust the shape of the mirror. And so even with that unexpectedly large impact, we were able to then adjust that mirror to take out most of the effects from the impact itself. And I don't want to make it sound dramatic. The way statistics work is we sort of had a distribution of expected impacts. And the one that we got, we did expect to get one of that size during our 5 to 10 year lifetime. We just didn't expect to get it within the first 4 months. But statistics works that way. That, that's just how it works. Maybe that was the one, and now we're going to go 10 years without one. So far, we haven't had any other ones that have concerned us, and so we're feeling pretty comfortable about it. But the telescope is exposed, and it was designed to be able to tolerate that for the lifetime of its mission.
We had a couple of questions about stars. One participant just wanted a basic definition. What is a star? And another asked about our own star, the sun, how far we are from it imploding.
Okay, so our sun is a star. A star is a very large, extremely hot ball of gas and plasma that is effectively burning elements to create the radiation that we see. And stars come in a variety of sizes. Their shapes are pretty much all round, but you can have small cold stars. We call them M dwarfs. You can have run-of-the-mill ordinary yellow stars like our sun. It's very typical. And you can also have very, very large, very bright stars like Rigel or Altair. And so part of the study of the lifetime of stars is the basic training that every astronomer gets, like I got at the Institute for Astronomy in Honolulu. So that's what stars are. Planets are things that orbit stars. There is, for extremely large planets, there's kind of a gray zone between what's a super large planet and what's a super small cold star. But it sort of boils down to whether or not there's enough mass to create fusion in the core. If there's enough mass to fuse elements and release energy, it's a star. If there isn't, it's a very large planet. So I hope that helps. Was there a second part that I forgot?
Well, there was a follow-up here. What is a nebula? And then the other part was how long our sun is good for.
Okay. Yeah, thanks. So nebula, apologies for throwing out this lingo. A nebula is a fancy word for a cloud of dust. That's it. A cloud of dust and gas all kind of swirling together. That is what we call a nebula. And they come in different shapes and sizes and forms. Some nebulae are circular, like the one I showed. Other nebulae make like long striations, like the cliffs that I showed you. But nebulosity just means fuzziness in an astronomical image, and it's gas and dust. And how old is our sun good for? We're good for like another couple billion years. I'm not worried about the sun. We got a long time to go.
All right, we have a question here. Can you elaborate on the physical basis of the arcing phenomenon seen in the deep field photos of galaxies?
Yeah, thank you for that question. I was worried I was running out of time, so I kind of skipped over that. Do you remember I said that is an image of a cluster of galaxies, and the galaxies are made up of billions of stars? There is so much mass there that mass bends space-time. So you have like it acts like a giant magnifying glass that's bending space-time. And so if you have a distant galaxy very, very far behind that cluster, the light from that galaxy is bent around the cluster. And that bending process and the way the mass is distributed in the galaxy gives rise to those arc-like shapes. And if you looked carefully, they kind of make a circular pattern around the galaxy and the galaxy cluster. And by using those arcs and their distribution and their shape, we can actually map out the mass of the galaxy cluster itself. So those arcs are caused by the actual bending of space-time by the cluster of galaxies, which I just love saying that. I think that's cool.
Sorry, forgot to unmute myself. We'll invite anyone who would like to unmute themselves at this point and ask a question directly. You can. You mentioned the up-and-coming scientists, and I wonder how important was the doctoral programs around the country and in this James Webb Space Telescope program. You talked about it being a 20-year project for you. Have you seen people who started as students and worked up to the point where they're involved as research scientists on the project?
Yeah, absolutely. Whenever you've got a program that is like 20 years in duration, you know, you're looking at generations of young students, right? 20 years is, I don't know, maybe my time in Honolulu was 5.5 years. So, you know, 4 generations of graduate students. I will share with you that I and many of our fellow scientists who are working on this program approached James Webb Space Telescope not as a telescope for us, but as a telescope for the next generation. And I was motivated to join this project because I got to use the Hubble Space Telescope as a young postdoc. And I had nothing to do with building it or anything. And it was just there for me to use and do amazing science. And so I felt it was important that my generation therefore build the next generation for those young people. They don't need to have built it. We built it for them. And so I gave away most of my time as an interdisciplinary scientist. I got 100 hours of guaranteed time on the telescope. And I gave it all away to mostly young scientists. In fact, I have a postdoc right now, and I have a tiny bit of time left over from the first year, and I'm giving all of it to my postdoc. Just because I just think that's what we have a responsibility, I believe, to make sure that our next generation of young people has access to the kinds of state-of-the-art tools that we did, and the state-of-the-art changes. So I hope that answers that question. I see that, Roy, you have your hand up?
Yeah, I just want to add to that great answer that among the people who are some of the first programs on James Webb are people like Dale Kachevsky, who was a graduate student in IFA, graduated 8 or 10 years ago. Jehan Kartaltepe, she may have been an ARCS scholar, is also from the IFA. Caitlin Casey, who was a Hubble fellow here. So many young astronomers who got their PhDs of an order of 5 to 10 years ago here in Hawaii are among the people doing some of the first large programs, especially in galaxy evolution, but also in extrasolar planets. Mike Liu, one of our faculty, was on this recent exoplanet release that came out with the image of this multi-Jupiter mass planet around HD 1116345, the phone number, right? So there's a lot of involvement of young people doing big programs on JWST.
As the advising scientist, how did you decide between the myriad of proposals for telescope time?
Yeah, the process for choosing who gets to use James Webb Space Telescope is based on a process that we've developed over the decades with the Hubble Space Telescope. So guaranteed time, like I have, is a special category of time that is given to the instrument scientists, the people who built the instruments, and people like me and a few other people who have been working on the project for 20 years. The bulk of the time regularly used is what we call guest observer program. And anybody in the world can apply to be an observer with James Webb Space Telescope or Hubble or any of Aura's other telescopes. What we do with that is we take these proposals, and they must be written in an anonymous fashion. Nobody knows who is writing them. And we submit them. We typically get for the first year, we get 1,000 proposals. That is the number. It's like 1,000 proposals to use Hubble or JWST in a year. And so we set up teams of experts in various fields, and we give them all the solar system proposals go to one person, all the galaxy evolution proposals go to another team, the exoplanet, they go to a team, and the team evaluates the science proposal, but they don't know who has proposed it. Everything is anonymous. And we have done that because we've learned with 30 years of Hubble that we saw biases. We saw biases in our selection processes. Women were not getting as much time as they were requesting. We saw that people from certain institutions or people with certain reputations tended to get time. out of proportion to how much they were requesting. And so we tried a whole bunch of different things. We tried just putting initials, but that didn't work because everybody knows who H.B. Hammel is, right? We tried moving the names off of the front page, and we eventually teamed up with social scientists who study intrinsic bias in systems like these. And eventually, the recommendation was you have to go dual, fully anonymous. And once we did that, so interesting, suddenly the gender statistics started to even out. And perhaps more importantly, we started to see first-time proposals. People who had never gotten time before were suddenly getting time. And institutions that had never gotten time before suddenly were getting time. And so, this has been a really very successful endeavor to try to mitigate the intrinsic biases that we have when we're reviewing things. And NASA is starting to adopt it. NSF is considering adopting it. Most of the major other telescopes now have moved to this dual anonymous process. So if you have a good idea and you can justify it and convince a cohort of your peers that you need JWST to do the science, you can get the time. That's how it works. It's a meritocracy now. So democracy, democratizing science.
That's great to hear. We have a question in the chat. Will JWST contribute to the question of dark matter and what it's doing in the universe?
Oh, yeah, I'm sure that it will. Yeah. That's not my field of expertise, so I'm not going to be able to give you a super good coherent answer on that. I do know that one example that I can share with you is, you remember when I was talking about how we can use the arcs around that the cluster of galaxies to map out the mass of the galaxy? We can compare the mass that we're mapping with the visible light that we see. And there's usually a deficit, and that deficit is the dark matter in that galaxy cluster. And by the details of how you map out the mass, you can map out where the dark matter is in the galaxy cluster. So that's one example of how we will be using the information from Webb to study dark matter. I'm sure there are many other examples that I'm just simply not familiar with because it's not my specialty.
Invite anyone else to ask a question. I guess you covered it all very well.
Those were a lot of good questions. Thank you very much.
So what's next for you? Just continuing to analyze data?
Yeah, I'm working with my team. My team is busy analyzing the data, and I'm just sort of helping, facilitating, getting that data out to the public. And my job right now as Vice President for Science at Aura is to help ensure the next generation of fabulous facilities is available. Our community, Astronomy, every 10 years we do a survey of our field and ask, what have we learned? What do we know? Where do we need to go? And our big giant facilities have been products of this survey activity. And last year we completed another decadal survey, and we are already thinking, I mean, I know this sounds crazy. We just launched JWST, but we're already thinking about the next facility that we want to build. And the driving force behind that is we want to find out if there's life out there in the universe, aside from in our solar system. JWST is not the tool to do that. I mean, it'll help, it'll contribute a lot of exoplanet science, but when it was being designed and built, we hadn't even discovered exoplanets yet. It's taken that long to build it. So the tool that we will need to really answer that question is, are we alone in the universe? And how did our universe come to be habitable if we find life elsewhere? That's going to take another telescope that's even bigger than JWST. Honestly, it has to be able to do this sensitive exoplanet characterization of enough exoplanets to make a really meaningful statistical argument about life. So working on that is part of what I do. And I also, I help ensure that the facilities that we currently operate for NASA, like Webb and Hubble, and also for the NSF, like the Gemini Observatory on Mauna Kea and down in Chile, and our new telescope we're building down in Chile called the Rubin Observatory. My job is to help ensure that those telescopes are scientifically productive and available to the broad community to continue all the astrophysics that we want to do as a country.
I have heard the question raised about the role of ground-based astronomy, given the advances we have with space telescopes. And if so, why are ground-based instruments still important?
Oh yeah, they're extremely important. The kinds of things you can do on the ground are far more flexible than we can do in space. It's very expensive to go to space, and we can't afford to put a lot of different telescopes up there. We don't use just one kind of telescope. We have telescopes like Hubble and Webb, which are sort of extremely high resolution, narrow beam telescopes. But we're now also building on the ground very wide field telescopes that allow us to take large pictures of the sky. And we have telescopes that are focused on specific types of objects, like searching for exoplanets. There are telescopes that do just that. And there are, a myriad other types of telescopes. So I kind of liken it to a toolbox. To do astronomy, you can't just have one tool. I mean, that's be like trying to build a house with a screwdriver. You can't do that. You need a saw, and you need a wrench, and you need nails, and you need all kinds of other things to build a house. And to do astronomy, you need an X-ray telescope, and you need a ground-based wide field telescope, and you need a deep field infrared telescope like Webb. All of these are different ways of sensing the universe, and they all work together in different ways. So the ground-based telescopes are still extraordinarily important in the field of astronomy. Pick any field, pick planetary science, my field. I mean, I need the IRTF, the NASA IRTF on Mauna Kea to do certain kinds of follow-up asteroid work. If I want to do high-resolution visible imaging of the planet Neptune, the telescope is Hubble. But if I want near infrared imaging, the telescope is the Keck Observatory on Mauna Kea. And if I want mid-infrared, it's now JWST. All of these are different ways of sensing the same object. They all work together to help us understand these astrophysical objects.
We have a question about the Alfonso Serrano telescope. Is that one that Aura is involved with?
No, I don't recognize the name. I'm sorry.
Okay, Sherry, do you want to?
It was the one that they put up last year. Peter Schorb from Caltech. He's the one that was involved with that, and they discovered the black hole.
Is it part of the Event Horizon Telescope where they
Yes.
had a network
Yes.
of telescopes all the way around the world?
Yes,
Okay.
yes.
Okay, yeah. Yeah, the Event Horizon Telescope was a sort of a catch name for a series of telescopes all the way around the world that worked together as one giant telescope to look at, to image a black hole environment. Yeah, so that was a very neat result. That was the NSF funded facilities to do that.
Okay.
Tell us a little bit about your team.
About what?
About your team.
My team?
Yeah.
My team, Team Solar System. That's what we call ourselves. JWST Team Solar System. I have, there's about 12 leads for different things. There's a giant planets lead, a Mars lead. Kuiper belt objects are kind of shared with the other instruments. Comets lead, an asteroids lead, a near Earth asteroids lead. These are all young people who I have offered this time to. I kind of spent years cultivating my planetary science community and explaining what JWST was and how we could use it. And then I said, I have all this time, 100 hours. people tell me what you want to do. And so people put together proposals for ideas. And I worked with a partner, Stephanie Milam, Dr. Stephanie Milam at Goddard Space Flight Center, who is the deputy project scientist for planetary observations at Goddard. And she and I together took all their ideas and tried sort of shoehorned them in to my 100 hours to try to get a sampler of the solar system. I wanted to use my time on JWST to really demonstrate the kind of extremes that we could do with Webb. The brightest things in the solar system, the faintest objects in the solar system, the fastest moving objects in the solar system, faint things next to bright things, like I showed you with the rings of Jupiter, and a few other ideas that were sometimes a little challenging and pushing the capabilities. I wanted to do that though, so that any other solar system science, when they had an idea, we would have some supporting data to show them what the possibilities were. And so put together a big program, and it's all starting to come out now. Like I said, just stay tuned over the next couple of weeks. You'll see some more results coming out. There is another solar system program called an Early Release Science Program that's run by Imke de Pater and Thierry Fouché. She's from Berkeley. He's from University of Paris, Manoa. And they are studying the Jupiter system specifically. And so we are working collaboratively with them. My Jupiter team is working with that Jupiter team. So we're covering, if you have a favorite solar system object, I can let you know if we're going to be observing it. And then there are many guest observer programs for solar system objects as well. So my team isn't the only team that's doing this, but there's a whole lot of people. And so I said I had about 12 leads, and then each of them has a team underneath them. So maybe about 50 people altogether on my team working with our JWST time. So I'm just so excited about it. I mean, I had this dream in 2002. I had a dream, I feel like Martin Luther King Jr. I have a dream. I had a dream that we would be able to do this. And my dream is coming true. So it's really very exciting time for me personally to see that happen.
So these are young people from various institutions, it sounds like.
Yeah, all over the US and even in countries in Europe as well. The lead of my Giant Planets program is a young scientist named Lee Fletcher at the University of Leicester. He's terrific, absolutely terrific.
We did have a question about any social media you have people could follow. So if you want to email me links, we will distribute that following. And I did neglect to ask you your permission to record this session and share it on our YouTube channel. So now I've put you on the spot, but if someone would give away 100 hours of prime telescope time, could hardly turn that down.
Yeah.
But I hear another question in the background there. No. What will Team Kuiper Belt come up with?
Oh yeah, Team Kuiper Belt. Kuiper Belt is going to be awesome with JWST. The Kuiper Belt objects in the guaranteed time program, my program, plus the other instrument teams, we are all sharing our time together. It's all being coordinated by John Stansberry at the Space Telescope Science Institute. So pretty much any Kuiper Belt object that has a name, like Sedna, Quaoar, Makemake, whatever your favorite Kuiper Belt objects are, Pluto, Kuiper Belt object, that is all part of our large team Kuiper Belt object group. And so Varuna, I'm just Orcus, Eris, Dysnomia, any Kuiper Belt object that's got a name, we're likely to be observing it. In addition to that, Noemi Pinella Alonso proposed, as part of the guest observer program, a large program to look at dozens of Kuiper Belt objects. I think 58 different Kuiper Belt objects. And so that was the largest solar system guest observer program, was to look at Kuiper Belt objects and to look at their spectra specifically. We're trying to look, for those of you who are not familiar with the Kuiper Belt, it's a cloud of objects that is at the orbit of Neptune and outside of Neptune. Sort of like the asteroid belt is in the inner solar system between Mars and Jupiter. That's a collection of rocks. This is a collection of icy bodies outside the orbit of Neptune. And there's thousands of them known, and they're cold and they're faint and they're small. They are perfect for JWST. They're like the prime target. So over the course of the next year, there will be a lot of Kuiper Belt science being done. I will share that Kuiper Belt science is the one part of the solar system program, my solar system program, that is not immediately available to the public. Aside from Kuiper Belt stuff, anytime one of my team members gets data, it goes into the archive at Space Telescope and is immediately accessible to the planetary community. I chose to make it that way so that the community could get that data right away. Kuiper Belt data are shared with my colleagues on the other instrument teams, and they did not want to make that publicly available immediately. All of it becomes available after 1 year, but they wanted to keep that 1 year period of time to allow them to have time to analyze it, in addition to all the calibration work that they have to do for their instruments. And so you may not see a lot of the Kuiper Belt stuff coming out for the first year, just because it's all being collected and analyzed, and it'll all be released later. There'll probably be a few come out, but I don't know exactly what the first ones are going to be. I hope that helps.
Well, thank you again. We have a number of messages in the chat. Very grateful for your time and the knowledge you shared with us, and for being willing to run over to answer some questions. So thank you, Dr. Hammel. Thank you, Roy, and thank you all who joined us today. We will send out the link once we have the video prepared, so you can rewatch any sections you wanted to refresh your knowledge on, or if you missed any of it. We have a couple more ARCS programs coming up in October. We'll talk about the Children's Healthy Living in the Pacific, our ARCS Scientist of the Year, that's her field. And in November, a piece on the stilts and taro fields in Hawaii. So you can see the vast range of science that ARCS supports, particularly in Hawaii, with interest in conservation and indigenous peoples and health issues. And of course, astronomy is one of our stellar, pun intended, programs at the University of Hawaii at Manoa. So thank you again all for joining us. We look forward to seeing you again. And Dr. Hammel, good luck and continued success with the James Webb Telescope. It must have been, what was it like that minute when it lifted off and it didn't explode and it didn't crash into the ocean? And I mean, were you biting your nails to the quick? Tell us about it.
It was very exciting, very nerve-wracking, but yeah, very exciting.
So 20 years of hard work paid off. Thanks again, and please join us again. Aloha.
Bye-bye.